All right, welcome back to the deep dive. Today we have a pretty ambitious goal.
We do, a big one.
We are going to try and demystify machine learning. I've got this stack of notes, and honestly, half of it looks like hieroglyphics.
It always does.
The mission today is to strip away what the experts call the cargo cult of jargon.
It's not as scary as it looks, I promise. We're going to try using the Feynman technique.
Okay, I like that.
Yeah, if we can't explain one of these algorithms to, say, a smart 12-year-old, then we don't really get it ourselves.
Perfect. So, big picture. For the longest time, coding was just rules. If this happens, then do that.
Explicit instructions.
But the sources all describe this huge shift to something called inductive pattern recognition.
Right. So instead of you writing the rules, you just give the computer a pile of data vectors, matrices, and the answer key. And you just tell it, you figure out the rules.
And it finds things we would miss.
It finds relationships a human would never, ever spot.
Okay, let's start simple then. Yeah, supervised learning, it's a huge part of machine learning. It's all about using labeled data where we already know the right answer to train a model. The model learns to map inputs to outputs. But, and this is crucial, it all hinges on the data. Garbage in, garbage out, as they say. Data quality is absolutely paramount.
Okay, right. So garbage in, garbage out. Let's unpack these models. If we're starting simple, where do we begin? Linear regression, maybe? That's the one where you're basically trying to draw the best fitting straight line through your data points on a graph, like pulling a string taut across them, minimizing those distances.
Exactly, yeah. The least squares method, technically.
Yeah.
Linear regression is, well, it's beautifully simple, very interpretable. We call it a white box model because you can see exactly how it's making predictions. Think about predicting salary based on years of experience. You can literally see the weight it gives to experience. Its strength is that clarity.
But it has limits, right? It assumes things are, well, linear.
Precisely. It assumes a straight line relationship, and the real world is often much messier than that. Doesn't always fit a neat line.
Okay, so if linear regression handles continuous stuff like salary, what about predicting categories like yes or no, spam or not spam? That's logistic regression, isn't it?
That's right. And what's fascinating here is how it does classification. It takes a linear model's output, sometimes called log odds, but then squishes it. It uses this function, the sigmoid function, that looks like an S shape. It forces the output into a probability, a value between 0 and 1.
Ah, okay. So not just yes or no, but maybe 95% chance this is spam, or a specific risk percentage for a disease.
Exactly. That probabilistic output is incredibly valuable for making nuanced decisions. Much more info than a simple binary yes-no.
Makes sense. Now, what if the relationships in the data aren't straight lines or simple S-curves? What if it's really complex nonlinear stuff? Decision trees come in here, yeah. They seem more like flowcharts, asking a series of if this, then that questions to split the data.
Yep, that's the core idea. It recursively partitions the data, asking questions at each step like, is feature X greater than value Y? Trying to create groups or leaves that are as pure as possible, meaning ideally each final group contains data points of only one class. We measure that purity or lack thereof using things like Janey impurity, trying to minimize the mix-up.
And the big plus is you can follow the path, right? See the logic.
Totally. Very interpretable. But, here comes the downside. They were notoriously prone to overfitting.
Overfitting? That's like memorizing the training examples, including all the random noise, instead of learning the actual underlying pattern.
You got it. Like a student who memorizes answers but doesn't understand the concepts. It performs great on data it's seen, but falls apart on new, unseen data. Doesn't generalize well.
That sounds like a big problem. So how do we stop these models from just memorizing everything? How do we, discipline them?
That's where regularization comes into play. This is really interesting stuff. Regularization basically adds a penalty to the model based on its complexity, usually related to the size of its coefficients or weights.
A penalty for being too complex?
Sort of, yeah. Two common types are lasso, or L1, and ridge, or L2. Think of it geometrically. Lasso uses a penalty that often forces some coefficients to become exactly 0.
0. So it kicks features out.
Exactly. It performs feature selection, which is super useful. Ridge, on the other hand, uses a penalty that shrinks all coefficients towards 0, but rarely makes them exactly 0. It's good for handling situations where your input features are highly correlated.
Okay, so ways to keep models in check. What about combining models? I hear about ensemble techniques, the idea that lots of simple models together can be better than one complex one, the wisdom of crowds.
That's a perfect way to put it. Ensemble methods combine multiple weak learners to create a single strong learner. And there are two main flavors. First, there's bagging. Think of a random forest. It builds multiple decision trees independently on different subsets of the data and then averages their predictions or takes a majority vote. It works in parallel, reducing the model's variance, making it less sensitive to the specific training data.
Okay, parallel processing. What's the other flavor?
That's boosting. This is sequential. Imagine a student working with a tutor. The first model tries to solve the problem, gets some things wrong. The next model focuses specifically on the mistakes the previous one made. Each subsequent model pays more attention to the errors, step by step, trying to reduce the overall bias. Gradient boosting is a key example here.
And isn't there one called XGBoost that always seems to pop up?
Ah, yes. XGBoost is essentially a supercharged, highly optimized version of gradient boosting. It's got built-in regularization, handles missing data well, and is computationally very efficient. That's why it often dominates data science competitions. It's very powerful.
Got it. Okay, one more I wanted to ask about. Naïve Bayes. The name Naïve sounds not great. Why naive?
Yeah, it does sound a bit suspect. It's based on Bayes' theorem, which is solid probability theory, but it makes a very strong naive assumption that all the input features are independent of each other given the class.
Independent. But features in the real world are often related, aren't they? How can it work if it assumes something that's usually wrong?
That's the counterintuitive part. It turns out that even though that independence assumption is almost always technically false, the algorithm often works surprisingly well in practice. Especially for things like text classification, spam filters are a classic example. Its simplicity makes it incredibly fast and efficient computationally. You just need to handle potential issues like the zero frequency problem. What happens if you see a word in testing you never saw in training? But there are simple fixes for that.
Wow. Okay, so we've covered quite a range, from simple lines to complex ensembles and even naive approaches. When you're faced with a problem, how do you choose? It sounds like there's no single best algorithm.
Absolutely not. There's no silver bullet. It's always a trade-off. You have models like linear regression, logistic regression, decision trees, even naive Bayes. They tend to be more interpretable. You can peek inside and understand why they're making certain predictions. Then you have models like random forests and XGBoost, which often give you higher predictive accuracy, sometimes significantly so, but they can be more like black boxes. Harder to understand the internal logic.
So it depends on the job, interpretability versus accuracy.
Exactly. What does your data look like? What are your project's priorities? Do you need to explain the why behind predictions, maybe for regulatory reasons? Or is pure predictive power the main goal? That balance dictates your choice.
What a fascinating journey, really. From finding the best line to combining weak learners into something powerful. It's this constant balance, isn't it? Simplicity versus complexity.
It really is. And maybe here's something for you, the listener, to chew on. That complexity we often chase for better predictions. It frequently comes at the expense of being able to clearly understand why a decision is being made. So it really pushes us to think critically. How much transparency are we willing to sacrifice for performance? In machine learning, and maybe in other decisions too.
That's a great point. How much transparency versus performance? Definitely something to think about in how we all process information and tackle problems. Think of us as your shortcut to, well, really getting informed. Today, we're jumping into unsupervised learning algorithms. These are like data detectives finding hidden patterns, but without any predefined answers. Our goal. Break these complex ideas down, Feynman technique style, so you really get what makes them tick.
That's a great way to put it. You know, I often think of Sir Isaac Newton and the apple. He didn't get data labeled gravity. He just observed, asked questions, and inferred the laws himself. That's unsupervised learning in a nutshell. It's discovery, finding structure before you even know exactly what prediction you want to make.
That really frames it well.
Yeah.
So, okay, how do we start finding these patterns? Clustering seems like a big one, right? Grouping similar things together.
Absolutely. And K-means is probably the most famous. Think center of the crowd. It finds the center, pulls points towards it, recalculates the center with this little two-step dance. You see it everywhere. Customer segmentation, even image compression, grouping similar colors.
K-means sounds pretty efficient then? But what are the catches? Like you have to tell it how many groups, and do they need to be, I don't know, certain shapes?
Yeah, exactly. It's fast, but you do need to specify K, the number of clusters up front. And it definitely prefers clusters that are kind of spherical and roughly the same size. If your data looks different, maybe long and thin clusters or different sizes, K-means might struggle a bit.
Okay, so if K-means has those limits, what's next? You mentioned DBSCAN before, something about density?
Right, DBSCAN. It takes a totally different approach. Instead of centers, it looks for dense regions. It uses two parameters, epsilon, that's like a search radius around a point, and minpeats, the minimum number of neighbors needed to be considered core. This lets it find clusters that aren't just round, they can be any shape. And crucially, it can identify points that are all alone as noise.
Noise, so like outliers, things that don't fit.
Exactly, which makes it fantastic for anomaly detection. Think finding weird credit card transactions, that sort of thing.
And you don't need to tell it K beforehand. That sounds really useful.
No K needed, which is a big plus. The trade-off. Tuning epsilon and min ports can be, well, a bit tricky sometimes. Especially if you have lots and lots of dimensions, density gets weird.
Right, high dimensions. We should come back to that. But first, there's another clustering type, hierarchical.
Ah, yes, hierarchical clustering. Think of building a family tree, but for your data points. It starts with every point as its own tiny cluster, then merges the closest ones step by step. You get this visual called a dendrogram, the tree diagram.
Okay, like a branching structure showing who merged with whom.
Precisely. And different linkage methods decide what closest means when you merge clusters. Like Ward's method tries to keep the merged clusters nice and evenly sized, so it's good for things like biological taxonomy or, again, market segmentation maybe.
And the cool thing with the dendrogram is you can kind of decide later how many clusters you want just by looking at the tree.
That's a huge advantage. You run it once, get the tree, then decide where to cut it to get your clusters. But the downside is it can get computationally heavy. For really massive data sets, tracking all those potential merges takes time. It starts with every point as its own tiny cluster, then merges the closest ones step by step. You get this visual called a dendrogram, the tree diagram.
Okay, like a branching structure showing who merged with whom.
Precisely. And different linkage methods decide what closest means when you merge clusters. Like Ward's method tries to keep the merged clusters nice and evenly sized, so it's good for things like biological taxonomy or, again, market segmentation maybe.
And the cool thing with the dendrogram is you can kind of decide later how many clusters you want just by looking at the tree.
That's a huge advantage. You run it once, get the tree, then decide where to cut it to get your clusters. But the downside is it can get computationally heavy. For really massive data sets, tracking all those potential merges takes time.
Okay, so that covers finding groups. But what if the data itself is just too much? Too many features, too complex to even start?
That's a perfect lead-in to dimensionality reduction. We need ways to simplify. And the classic here is principal component analysis, PCA. Its goal is to find new axes, principal components that capture the most variance, the most information in your data. Imagine squashing your data onto a line or a plane while losing the least amount of spread.
So it simplifies things, makes it easier to maybe visualize or process, like for image compression again.
Exactly. Visualization, compression, and it's a key weapon against the curse of dimensionality.
Okay, PCA sounds powerful for simplifying. But interpreting those new principal components, are they easy to explain? Like, what do they mean?
That's the rub. They're mathematically efficient, capturing variance, but they're abstract combinations of your original features. So telling a business user what principal component 1 means can be tricky. It shows separation, but maybe not the why in simple terms. And just quickly, while we're here, it's worth mentioning LDA, linear discriminant analysis. It also reduces dimensions, but it's actually supervised.
Ah, right. So LDA needs labels. How does its goal differ from PCA then, if both reduce dimensions?
Totally different goal. PCA just looks for the directions of maximum variance in the data, regardless of labels. It's exploratory. LDA, because it has the labels, specifically tries to find the dimensions that best separate those known classes. Think improving a classification model, like for credit risk, where you know who defaulted and who didn't. PCA explores, LDA separates known groups.
Got it. PCA for exploring structure, LDA for enhancing classification. Okay, let's shift to some maybe foundational ideas that pop up across these methods.
Sure, like k-nearest neighbors, KNN, usually taught as supervised, right? Find the k closest labeled points and vote.
Yeah, for classification or regression, but unsupervised.
Well, the core idea of finding neighbors is super useful without labels, too. For anomaly detection, if a point's average distance to its k-neighbors is really high, maybe it's an outlier, right? It's far from everyone. Or even filling in missing data, look at the values of the nearest neighbors and estimate.
So the basic mechanism of finding neighbors can be used in creative, unsupervised ways. That's neat.
It really highlights understanding the core idea. And speaking of neighbors and distances, that brings us to the curse of dimensionality you mentioned.
Right. The curse. What actually is that? Sounds ominous.
It is, a bit. Basically, as you add more and more dimensions or features, the space your data lives in gets incredibly vast and empty, really sparse. Counterintuitively, everything starts to seem far away from everything else. The concept of a close neighbor starts to break down.
So distance-based algorithms like KNN or even clustering, they just stop working well.
Pretty much. The distance has become less meaningful, which is why dimensionality reduction like PCA isn't just nice to have. Sometimes it's almost essential to make these algorithms work effectively in high dimensions.
Makes sense. And underlying all these distances, how we measure closeness itself matters, right? The metrics.
Absolutely fundamental. Euclidean distance is your straight line, as the crow flies. Good baseline, but sensitive to outliers. Assumes things are kind of Gaussian. Manhattan distance is like city blocks, only horizontal and vertical moves. Less sensitive to outliers, maybe better if data seems more Laplacian. And then cosine similarity just cares about the angle between data points, not the magnitude. Great for text data, where word counts might vary wildly, but the topic, the direction, is similar.
Wow, so choosing the metric isn't trivial. It's a core assumption about the data.
It really is. It shapes what similar means.
Okay, so with all these methods, k-means, DBSCAN, PCA, how do you tune them? In supervised learning, you have the right answers to check against. Here, you don't. So how do you know if it's good?
That is the million-dollar question in unsupervised learning. There's no single right answer or objective score like accuracy. It comes down to a mix of things. Heuristics, like looking for stable clusters. Domain knowledge. Does this grouping make sense in the real world? And ultimately, human judgment. Can you, the analyst or the user, derive useful insights or value from the patterns it reveals? The data scientist becomes more of a facilitator for discovery.
So we've really dived deep into this world of unsupervised learning. It's clearly more than just algorithms. It's a whole mindset about exploration and discovery in data.
Exactly. That lack of ground truth isn't just a challenge, it's the whole point, in a way. It's the opportunity. It lets us find structures, signals, connections in huge amounts of unlabeled data that we might never have even thought to look for. Truly hidden insights.
So maybe the final thought for you listening is, knowing these hidden structures exist, how might that change the kinds of questions you even think to ask about the world around you? Something to ponder.
Ever wondered how intelligent systems learn complex tasks? I mean, not from perfect instructions, but purely by experiencing their world.
Right.
Today, we're plunging into reinforcement learning, RL. It's this really fascinating area of machine learning. It's all about how agents learn to make sequential decisions, basically through trial and error.
Exactly. And our mission for you in this deep dive is, well, to cut through the noise, unpack the core mechanics of RL, and clarify why it's such a game changer for problems demanding optimal decisions over time. You should get some real aha moments about how these systems learn from often quite delayed feedback.
Okay, let's unpack that. Our sources really stress that reinforcement learning is, at its heart, concerned with an agent making a sequence of decisions.
Yeah, in an environment that's dynamic, maybe uncertain.
Right, and the goal is always maximizing some kind of cumulative reward signal.
And what makes RL so potent, I think, is that unlike systems you train on static pre-labeled data sets.
Like in supervised learning.
Precisely. RL actively discovers the best behavior through continuous interaction, trial and error. It's really uniquely suited for that sequential decision-making where the impact of an action isn't always immediately obvious.
Let's try and ground this. The classic analogy is training a dog, right? Dog's the agent, the living room is the environment. Actions like sit, get a reward, maybe a treat. But, for our deep dive, let's maybe pivot instantly to something more complex.
Yeah.
Think about an autonomous drone navigating a forest.
Okay, yeah.
Here, the state isn't just dogs sitting by the door. It's like this high-dimensional input of LiDAR data, GPS, camera feeds, much more complex.
That interactive loop, though, that defines RL, you always have these 5 core components.
Yeah.
The agent that's the decision maker.
Got it.
The environment, the external world it interacts with. The state that's its current perception of the world, like that drone's sensor data.
Right.
The action, what the agent chooses to do. And the reward, which is that immediate numerical feedback, good or bad.
Okay, so those are the building blocks. Agent, environment, state, action, reward. But how does it actually decide what action to take in a given state? That gets us to the policy, right?
Exactly. The policy is essentially the agent's master strategy. Think of it as a map from states to actions.
A map, okay.
And policies can be deterministic, like always do this action in this state. Or they can be stochastic.
Stochastic. So probabilistic.
Yeah, providing a probability distribution over actions. Deterministic is fine if the world is perfectly predictable.
But it rarely is.
Right. So stochastic policies are vital. They help with exploration, trying new things, and they're crucial in, say, adversarial settings like poker. If you're too predictable, you get exploited.
Okay, that makes sense. You need some randomness.
A bit, yeah, to learn robustly.
So building on that policy idea,
Yeah.
if a reward is like a single paycheck you get right now, then the value function sounds like it's more about the long game, like a financial forecast for the next decade, the total expected reward down the line.
That's a great way to put it. It's this forward-looking perspective. It's often formalized by something called the Bellman equation, which is, well, it's really the backbone of many RL algorithms.
Why is it so central?
Because it lets us break down this huge, complex, long-term optimization problem into smaller, recursive steps. It essentially says the best value of being in a state now is the immediate reward you get, plus the discounted best value of whatever state you end up in next.
Discounted, meaning future rewards are worth a bit less than immediate ones.
Exactly. It encourages prioritizing achieving goals sooner rather than later, and it also keeps the math as manageable. It helps the agent weigh long-term gains against short-term ones.
So as the agent is learning, refining its policy, figuring out these values, it hits this classic problem, right? The exploration-exploitation dilemma.
Ah, yes. The ultimate dilemma, isn't it? It's like finding a restaurant you absolutely love.
Yeah.
Do you just keep going back, exploiting that knowledge? Or do you explore that new place across town that might be even better, but could also be terrible?
Right. The risk versus the known reward.
Precisely. That balancing act. Exploiting what you know works versus exploring new possibilities for potentially much bigger payoffs. Getting that balance right is absolutely core to learning optimally in RL. Too much of either isn't good.
Okay, that provides a really good picture of the mechanics inside RL. But, stepping back, we already have supervised learning, unsupervised learning. What is it fundamentally that makes RL stand out? What problems can it solve that the others can't really touch?
The key differentiator, I'd say, is the credit assignment problem.
Credit assignment. Explain that.
Okay. In supervised learning, the feedback is instant. You show it a cat picture, it says dog, you immediately say, no, that's a cat. The feedback is right there, tied to that specific input.
Got it. Direct link.
But in RL, imagine playing chess. You make a brilliant move on turn 10, but you might not actually win the game until turn 50. The profound challenge is figuring out which of the many actions you took before that win were actually responsible for it. Was it that move on turn 10, or something on turn 35, or a combination? Assigning credit back in time to the right actions. That's tough.
Because the reward is so delayed.
Exactly. And this is precisely why techniques like Q-learning and temporal difference learning, or TD learning, are so fundamental in RL. They give us elegant ways to propagate that delayed reward signal back through the sequence of states and actions, even if we don't have a perfect model of how the environment works.
Oh, it's like learning a really complex skill.
Sequential delayed feedback and the algorithms designed to handle it, that's what truly makes RL unique.
And we see this playing out spectacularly in video games, right? They become this amazing sandbox for RL.
Oh, absolutely. I mean, from classic Atari games like Miss Pac-Man's Simple Actions, but millions of possible game states all the way up to DeepMind's AlphaGo Mastering Go.
Which has an astronomical number of states.
Astronomical. And OpenAI's Dota 2 AI. These RL agents learn strategies that are often at or even beyond human level. They frequently use deep neural networks now to handle the sheer complexity, approximating those policy and value functions by basically playing millions and millions of simulated games.
You mentioned something earlier about intentional imperfection in commercial games. That sounds counterintuitive. Isn't RL all about finding the optimal strategy? Does needing imperfection mean RL has limits? Or is it something else?
That's a really sharp question. It's less about a limitation in RL's ability to find the mathematically optimal path, and more a challenge in defining what optimal means when humans are involved. An AI that finds some obscure loophole to win every single time might be optimal according to its reward function, but it would be incredibly boring or frustrating for a human player.
Right, ruins the fun.
Exactly. So it's more an adaptation. Game designers carefully shape the reward signals, or sometimes they combine the learned RL behaviors with more predictable scripted actions. The goal shifts from pure mathematical optimality to creating an opponent that's engaging, challenging, maybe even feels fair, even if it's not technically playing perfectly. It reflects that the goal is often more nuanced than just winning.
That makes a lot of sense. So wrapping up then, reinforcement learning gives us this distinct Really powerful way for agents to learn the best policies just through interacting with their world.
And brilliantly balancing that need to explore new things with exploiting what already works, all to maximize that cumulative reward over the long haul.
And it's clever ways of tackling that credit assignment problem, handling delayed rewards, and adapting on the fly.
Yeah, it means the applications are just exploding well beyond games. We're seeing it increasingly in robotics, personalized medicine, complex financial modeling, sophisticated recommendation systems. It's really versatile.
We have covered a lot today. So, next time you see an AI making what looks like smart sequential decisions, maybe pause and consider that intricate dance. It's doing actions, states, rewards, exploration, exploitation, constantly learning.
It really is a fascinating process.
And maybe think about this. How might understanding this exploitation balance change how you approach learning new skills, or even making important decisions in your own life? Something to chew on.
Today, we're jumping into deep learning, or DL, which is, the engine behind pretty much every major AI breakthrough we see.
From your phone's camera to the huge language models.
Exactly. So our mission today is to get past the buzzwords and really figure out why this specific type of AI became so incredibly powerful.
And it's interesting because at its core, deep learning is really defined by its architecture. It's just multiple layers of computation, kind of inspired by the brain.
Inspired by the brain, right.
But the real game changer isn't the structure, it's what it can do. It can take in huge, messy piles of unstructured data images, text, sound, and just figure out the patterns for itself.
So it's this idea of depth then. How does just adding more and more layers actually change what the model can learn?
It enables something called hierarchical feature learning. You can think of it like a pyramid. The first few layers learn really basic stuff.
Like edges and colors in a picture.
Exactly. Simple edges, textures, that sort of thing. But then the deeper layers start combining those little pieces into much more complex concepts. Like it'll put edges together to see the curve of a wheel or the shape of an eye.
I see. So it builds understanding.
It builds understanding layer by layer. And the data on this is just undeniable. We saw a 152-layer network outperform an 18-layer one on the ImageNet challenge by almost 10 percentage points?
That's a huge difference. But if the core math, this thing called backpropagation, was figured out way back in the 1970s, were we just waiting around for better computers? Did we miss the boat for 30 years?
That's the million-dollar question, isn't it? And the failure wasn't really algorithmic. I mean, the math was solid. It was a resource bottleneck.
A resource bottleneck.
Yeah, they had this beautiful mathematical engine, but they had absolutely none of the fuel. They didn't have the massive data sets or the raw compute power. It was like having a Ferrari engine, but only bicycle fuel to run it on.
Okay, so the fuel had to arrive, and that was the ImageNet project, right?
That was the catalyst. Between 2009 and 2012, Fei-Fei Li's team saw this exact problem, this data deficit, and they built ImageNet. We're talking 12 million labeled images.
A massive undertaking.
And that set the stage for what we call the AlexNet moment in 2012. They used GPUs, graphics cards, to just power through that data. And it didn't just improve the result, it slashed the error rate. It proved that scaling up data and compute wasn't just helpful, it was everything.
So they had the fuel and the engine. What was next?
Well, even with the power, the process was still a bit inefficient. It needed a better lubricant, you could say. And that innovation was the rectified linear unit, or ReLU.
ReLU.
Sounds technical. But the idea is simple. It's just a more efficient on-off switch for the artificial neurons. It stopped the deep networks from seizing up during training, which is what made training a 152-layer network even possible.
Okay, that makes sense for images. But what about something messy, like a conversation or just a long piece of text? I've heard about this vanishing gradient problem.
Right. With sequential data, older networks, they had terrible short-term memory. A signal from the beginning of a paragraph would just fade away or vanish by the end.
So it would forget the context.
Completely. And that's what led to things like LSTMs and GRUs. They have these spiralized little mechanisms, like a forget gate, that let the network very deliberately decide what old information is important to keep. That finally cracked the long-term memory problem.
And that whole line of thinking led us to where we are now with the transformer architecture from 2017. What was the big leap there?
It completely threw out sequential processing.
Yeah.
Instead of reading word by word, the transformer uses something called the self-attention mechanism to look at every word at the same time. It's massively parallel.
And self-attention is the core of every big language model today. So what is it in simple terms?
The best analogy is that for every single word, it runs a quick search across the entire sentence to see how relevant every other word is. It uses these things called query, key, and value vectors to weigh connections.
So it creates a global context.
An enforced global context instantly. It knows how the first word relates to the last word, all at once. That's its superpower.
So if you put it all together, deep learning's success wasn't one thing.
No, it's a perfect storm. It's a symbiotic relationship between, the mathematical insights from decades ago, the explosion of big data, and the sheer power of modern hardware like GPUs.
So here's the final thought to leave you with. While these DL models give us incredible performance in everything from medicine to self-driving cars, their complexity often turns them into complete black boxes. We know they work, but we don't always know why.
That's the trade-off.
And that's the critical challenge facing everyone in this field. We're constantly choosing performance over interpretability and figuring out how to balance those two things. Well, that's the next great deep dive.